Welcome to our video on the derivatives of exponential and logarithmic functions. We see exponential and log functions in many disciplines. They're used to create mathematical models of certain phenomena such as population growth, radioactive decay, seismic activity, compound interest, alkalinity and acidity in chemistry, decibel measures of sound, and others. Log and exponential functions are inverses of each other, and they're used to solve equations involving one or the other. This use would be similar to how we would square to undo a square root or take the square root to undo a square in the process of solving an equation. Also, log scales are useful for graphing data, which covers orders of magnitude, meaning you wouldn't be able to fit it on a piece of graph paper with a linear scale, so log scales are used for graphing certain types of data sets that have a very large span. In studying logarithmic and exponential equations, we encounter the natural base e. E is called Euler's number. E is a mathematical constant, which is approximately equal to this decimal number here. However, it's irrational, like another mathematical constant, pi, which means it's a non-repeating, non-terminating decimal number, a real number. So this may not make a whole lot of sense, but this definition here says that E is defined as the unique positive base whose graph y is equal to e to the x has a slope of 1 at x is equal to 0. So the slope of the tangent line at x is equal to 0 will equal 1. Okay, this fact here is used in deriving the derivative of e to the x, which we're not going to have time to get into. It's beyond the scope of what we're going to do here. The natural log function is a log which has a base e. So it's written ln. The natural log of x is log to the base e of x. So the natural log and e to the x are inverse functions, and they undo one another. So if you raise e to the log base e of x, written like this, you will return to x. So they undo each other, and this is something we've seen before when we're solving exponential equations. So e to the x, the function e to the x, has a very well-behaved derivative. The derivative of e to the x is also e to the x. F of x is equal to e to the x. F prime of x is equal to e to the x. So as I mentioned in the last slide, this can be proven by using the limit definition of the derivative and this fact here that the slope of the tangent line at x is equal to 0 is 1. This proof is included in our online textbook. So in the text box here, the derivative of e to the x is e to the x. We're also going to need our log properties from pre-calculus. So there's the product rule for logs. So if you have a log to any base of a product of m and n, m being some expression and n being another expression, you can break this into a sum of log base b of m plus log base b of n. So they have to be inside the parentheses, and this b right here will also show up here and up here. So multiplication and addition are related in logs just like they are with exponents. And then we have the quotient rule, where if we take log to the base b of a quotient, the division is related to subtraction, just like it is with exponents. And then we have the power rule for logs, which says if you take log to the base b of an expression raised to a power p, this is equivalent to multiplying by that power in front and removing it from its position right here. So you take it from this exponent position and you put it in front. And this helps us with some simplification, and we're going to need to use these properties along the way here. So here's our table of derivative formulas for exponentials and logs, and we're going to utilize these in the examples to follow. So I'm not going to prove any of these. The proofs are available in your online textbook, but these derivatives here are obtained using implicit differentiation. So for example 1, I've written the formulas on top that we're going to use from the table of formulas in the earlier part of this presentation. So part A says I'm taking the derivative of the natural log of 2x squared. So I'm going to use the first formula here. So let's just call that y prime. Remember, y prime is also sometimes called dy dx. Sometimes y prime is just a shorter way of saying it. So I've got 1 over 2x squared, and I'm going to have to use the chain rule here because I don't have just a plain x right there. So the derivative of 2x squared, multiplying by that. So this is 1 over 2x squared times 4x. So 4x over 2x squared. So that's going to reduce to 2 over x. So for the second one, I'm going to use the derivative of a to the x is a to the x ln of a. So here my a is 8. So y prime will be 8 to the x. Natural log of a, like I said, was 8. So this one isn't much work. And the last one, I'm going to utilize the formula on the right here. So I've got 3 times the derivative of e to the x, which is just e to the x. So we should call this y. This is y prime. And the center term, using the power rule, would be 10x. Derivative of negative 8 would just be 0. So this is our derivative here. So for example 2, we're going to use the product rule. So we've got a natural log in there again. So let's just write that formula down again. So here's our formula. So now I'm going to use the product rule here. So I've got a 2-piece y here multiplied together. So the first, this is going to be y prime, first times the derivative of the second. So I have a non-x argument there, so I have to multiply it by the derivative of 5x squared, which is 10x. So that's the first times the derivative of the second, now plus the second times the derivative of the first. So I've got x cubed, the derivative of x cubed is 3x squared, and the derivative of 5 is 0. So we can simplify this a little bit. So we've got 10x, 5x squared, x cubed plus 5, and we'll put this out front. So we've got 2 over x. So let's extend the line here. And then 3x squared, natural log of 5x squared. So we'll just leave it like this. Of course, whenever you have numerators and denominators like that, it's possible to get it into a different form, but we're just going to leave it like this. So I wrote down the formula that we're going to be using to differentiate log base a of x. So a is your base, so my a is 3 in this case. So y prime is equal to 5 divided by x ln of 3 my a is 3, plus 5 times the derivative of e to the 2x, which would be e to the 2x, times the derivative of 2x, which would be 2. So y prime is 5 divided by x ln of 3 plus 10 times e to the 2x. So on this, we just have basically a multi-term exponent here to the e, but we're still going to use the same derivative formula. So y prime is equal to 6 e to the x, where our x is just this more complicated exponent here. And then we're going to multiply it. Let's just write this right here. We're going to write this beside it, derivative of that 4x cubed minus 5x squared. All right, so that's 6e to the 4x cubed minus 5x squared times 12x squared minus 10x. All right, so let's put that out front. We've got 6, 12x squared minus 10x times e to the 4x cubed minus 5x squared. So that's what we have. Now let's just leave it like that. We could distribute that 6 into that 12x squared minus 10x, but we'll just leave it in factored form. This one says find the equation of the tangent line to the function at the given point. So we're just going to differentiate the function. So that's just 10 minus 4 e to the x. That's what it is. And we're going to evaluate it at the point 0, 1. So we need f prime of 0. So that's 10 minus 4 e to the 0. So anything to the 0 power is 1. So this is 10 minus 4 times 1. So that's 10 minus 4. So that's 6. So the slope of the tangent line is 6. So using point slope formula, y minus 1 is 6, x minus 0. So that means y is equal to 6x plus 1. All right, so here's our slope. All right, and here's our derivative. So we're going to simplify this first using our log properties, and then we're going to differentiate. So first we've got a power right here, which we're going to put out in front, and then we have a quotient right here, which is related by subtraction. So we're going to simplify this equation first, and then we'll take the derivative. So I've got y is equal to 5 times the natural log of this quotient. And then that's equal to 5 times the natural log of the numerator minus the natural log of the denominator. So now I'm going to find the derivative. So I've got 1 over 3x cubed times the derivative of 3x cubed, which would be 9x squared. And then for the next one, 1 over 5x squared minus 1 times the derivative of 5x squared minus 1, which would be 10x. So then we just try to simplify this a little bit. 9x squared divided by 3x cubed, 10x divided by 5x squared minus 1. And then let's see if we want to do anything else to this. So let's reduce that fraction a little bit. So that would be 3 over x minus 10 divided by 5x squared minus 1. Of course, there's more that we could do to this, but let's just leave it like that. Okay, so on this example as well, we're going to simplify it using our log properties first, and then we'll differentiate. So I have a power here, so I'm going to put that out in front first. And as I'm writing this out, you can see that I have a quotient, which I know I can simplify using subtraction. So this is 3 times the natural log of the numerator minus the natural log of the denominator. And now I can differentiate each of those terms separately. So this is 1 over, and then take the derivative of x to the 4th. This is 1 over. Take the derivative of 4x squared plus 5. That would be 8x. Now we clean it up a little bit. 4x cubed divided by x to the 4th. 8x divided by 4x squared plus 5. And then we'll simplify that first fraction, and we'll get 4 over x, 8x over 4x squared plus 5. All right, so let's just leave it like that. So generally, I like to simplify things a little bit further, but I don't want this video to get too long. So if you need practice combining rationals, go ahead and take it down further than this. Okay, once again, we're going to simplify using log properties first. So I've got y is the natural log of 2x minus 5, 3x plus 8 to the 1/2 power. So that's the same thing as 1/2 times the natural log of this quotient. So I can keep going. So this is the natural log of the numerator minus the natural log of the denominator. And now I'm ready to take the derivative. So this is 1 over times the derivative of 2x minus 5. This is 1 over times the derivative of 3x plus 8. Right now I just clean it up a little bit. So that's 2 over. That's 3 over. Of course, we got a rational expression again, but we're not going to combine that. Let's just leave it like that. Like I said, if you need practice, you should go ahead and do the combining. But I'm trying to keep this video as short as possible. So this is our answer here. Okay, once again, we're going to simplify using log properties and then differentiate. So I've got y is the natural log of a product of 1, 2, 3 things. So multiplication and addition are related when we talk about logs and exponents. So I'm going to break this down into a sum of 3 parts. So this is the natural log of the first, x to the 4th, plus the natural log of this one, plus the natural log of this one. And now you can see I've got these powers here that I can put out in front, make it even more simplified. 4 ln of x, 8 ln of x minus 4, 5 ln of x cubed plus 6. All right, so now I'm going to differentiate. So that's 4 times 1 over x plus 8 times, let's just put the 8 there, 1 over x minus 4 times the derivative of x, which is just 1. So just put the 5 on the top. So 1 over x cubed plus 6 times the derivative of x cubed, which is 3x squared. So what I did there is, instead of putting the 4 out front and knowing that I'm going to eventually have to go and multiply it by the 1 that's on top, for these I just went ahead and put it on top because I knew it was going to wind up there anyway. In fact, you can start doing that now if you want to. All right. So now y prime is 4 over x plus 8 over x minus 4 plus 15x squared divided by x cubed plus 6. All right, so we're just going to leave it like that. We could combine that into one numerator and one denominator using our common denominator skills, but we're just going to leave it like this. So in this one, you can see we have a sign involved in this equation here. So we're going to differentiate f of x. So we're going to f prime of x here. The derivative of the sign is the cosine. So we have all of this here, which is the argument of the cosine. So now we have to multiply. We got to differentiate. Let's just write this. 16 ln of 2x. All right, so we got to differentiate that. So this is 5 times all of this. All right, so now let's go ahead and figure out that end part. All right, so I've got 16 times 1 over 2x times the derivative of 2x, which is just 2. Okay, so now we're going to clean this up a little bit here. So these 2's here, those will cancel. So we've got 5 cosine of 16 natural log of 2x times 16 over x. So that's 5 times 16, that's 80 cosine of 16 ln of 2x with an x in the denominator. All right, so this is f prime of x. So the next tool we have in this unit is called logarithmic differentiation. So this is used to simplify differentiation when we have a complicated product, quotient, or power. So what we do is we take the natural log of both sides, and then we'll simplify if we can using our log properties, and then we'll differentiate implicitly with respect to x so that we can then solve for dy dx. So let's try this. So with example 12, we've got 3x to the 5x. So that's not the same as something like 3x to the 5, where you can multiply 3 times 5 and drop the power down by 1. And that's because you have an x in the power. So we're going to use a different technique when we see this. So we're going to use logarithmic differentiation. So we take the ln of both sides, step 1, and then we simplify that using any log rules that will allow us to do any simplification. So I've got a product here, 3 times x raised to the 5x. So I can say I have the ln of 3 plus, because it's a product, it's connected to plus the ln of x to the 5x power. And then I could further say that this can be simplified one more time. This is the ln of 3 plus 5x, bring the power in front, ln of x. All right, so we've got it simplified with our log properties. Now we differentiate both sides. So we know the derivative of the ln of y is just 1 over y, and we're differentiating implicitly, so this is the times the derivative of y with respect to x. So then we're going to take the derivative, let's just write this out, of the ln of 3, and we're going to take the derivative of the product 5x ln of x. All right, so we already did the derivative on the left. All right, so now the derivative of ln of 3, well, ln of 3 is a constant, so this is going to be 0. So then I've got the derivative of a product here, 5x times ln of x, so I have to use the product rule. So that's first times the derivative of the second, but the derivative of the natural log of x is just 1 over x, plus the second times the derivative of the first, which is 5x, so the derivative of that is 5. So now what I have is 1 over y. So that's 5x over x, that's 5. And then this is 5 ln of x. All right, so the next step is to solve for dy dx. And this will be your derivative. So I have to multiply both sides by y. So my y will be here now. But I know what y is from up here. Y is 3x to the 5x. So I put that here. 3x to the 5x. 5 plus 5 ln of x. All right, I'm done. This is my derivative using logarithmic differentiation. So here I go again. I'm going to differentiate this function using logarithmic differentiation, and then I'm going to evaluate it at 2. So the first thing we're going to do is take the log of both sides. So this is y. So the natural log of y equals the natural log of 3x to the ln of x. Now I'm going to rewrite using my log properties wherever I can. So this right here is a product. Products are connected by addition. So this is the same thing as ln of y is equal to the natural log of 3 plus the natural log of x to the ln of x. All right, so I can see that I have a power here, ln of x, that I can pull out in front of the ln here. So one more thing I see I can do, ln of 3, bring the power of ln of x down here in front, and I've got the ln of x times the ln of x. All right, so now I'm going to differentiate both sides. So let's just write that. Differentiating, all right, let's make that a little neater. Derivative with respect to x of the ln of y, derivative with respect to x of the ln of 3, plus the derivative with respect to x of this product here. All right, so we know the derivative of the ln of y is 1 over y dy dx. So we know the derivative of a constant, ln of 3 is a constant, is 0, so I'm not going to write that. This right here goes to 0. So now I've got to use the product rule. So I've got the first times the derivative of the second plus the second times the derivative of the first. So that's 1 over y dy dx is equal to ln of x over x plus ln of x over x. So that's two of those. So 1 over y dy dx is 2 ln of x over x. All right, so now I put y back in front there, which was 3x to the ln of x, and I'll have my derivative. So I'm multiplying both sides by y. So y was 3x ln of x from the original problem times 2 ln of x divided by x. All right, so there's not a whole lot we can do to improve that situation. See, we got a 3 and a 2 is a 6. Well, we can do that. We can call this 6x to the ln of x times ln of x divided by x. All right, and now we're asked to evaluate it at 2. So we're going to substitute 2 everywhere I have an x. So then I've got times the natural log of 2 divided by 2. So I've got 6 times this, which I can do in pieces, or I could type it in all at once without those dots. And if you do that in the calculator, you should get 3.362055. Right, so this is evaluated, and then my derivative was here before I did the well, let's go further. So here's my derivative with the 6, and here's my evaluated derivative, evaluated at 2, which I just typed into the calculator. So there's a lot we can do with this technique. Let's just do a little bit more. So I've got, once again, a complicated power situation. So I'm going to use logarithmic differentiation to differentiate this function here. So ln of both sides. First step. Use my simplification techniques for logs. I bring my power down in front. All right, so I'm going to start there. So I'm going to differentiate both sides now. So I know the derivative of the natural log of y is 1 over y dy dx. I'm differentiating implicitly. Remember, that's why I've got the dy dx there. Y is a function of x. All right, now I've got a product here. So I've got the first times the derivative of the second, which would be just 1 over the natural 1 over 6 plus e to the x times the derivative of 6 plus e to the x. That would be e to the x. So that's the first times the derivative of the second plus the second times the derivative of the first, which is just 1. All right, let's clean this up a little first. So I've got x e to the x in the numerator, 6 plus e to the x in the denominator. And then I've got the natural log of 6 plus e to the x. All right, so now I need to multiply both sides by y to solve for dy dx. Of course, y is simply from the very, very beginning, 6 plus e to the x to the x power. So that's y times all of this inside the bracket. And then, of course, it doesn't have to be square brackets. you could use smooth brackets, and that's what you'll most likely do. All right, so I've cleaned it up as best I can. I'm just going to leave it like that. That's just fine, and that's our derivative. Here's my last example. So you can use logarithmic differentiation on something that looks like this. So first thing we do is take the natural log of both sides. Natural log of all of this, 3x to the 4th plus 5 cubed, x to the 5th plus 4 to the 4th times 4x cubed. All right, so now I can go ahead and use my log properties. So I've got the natural log of the numerator minus, because I've got some division here, minus two things that are in the denominator, minus another thing, minus 4 natural log of 4x cubed. All right, so now I can take these powers here and put them out in front. This one is inside, so I can't do it there. So I've got ln of y, 3 ln of 3x to the 4th plus 5, 4 ln of x to the 5th plus 4, and then this one, 4x cubed. All right, so now I'm ready to take the derivative. So on the left, 1 over y dy dx. This would be 3 over 3x to the 4th plus 5 times the derivative of 3x to the 4th plus 5, which would be 12x cubed. So that got 4 over x to the 5th plus 4 times 5x to the 4th, which is the derivative of that denominator. 1 over 4x cubed times the derivative of 4x cubed, which is 12x squared. So I can see here that I'm going to have a 3 up top. Those are going to cancel. I'll just have 3 over x for that term. All right, so now let's go down to the next line, and I've got 1 over y, 36x cubed, 3x to the 4th plus 5, 20x to the 4th, x to the 5th plus 4, minus 3 over x. Last step, I multiply through by y, and I'll have my derivative, dy dx. So my y is the original equation we were given on the right-hand side. So my y is 3x to the 4th plus 5 cubed, x to the 5th plus 4 to the 4th, 4x cubed. Okay, that's my y times all of this stuff here. Beside it. All right, now this is your derivative. Now, of course, you could combine all of this into one fraction with the numerator and denominator and see if anything possibly could cancel, or you could just leave it like this. Typically we leave them like this, but you know, it's up to you whether you want to practice your simplification skills and get this down smaller. So this wraps up our section on derivatives of exponential and log functions. You should have enough information, enough examples to go by to work on some of our problem sets.